In the previous video, we saw how function decorators use functions as input data to manipulate. In this video, we'll take a look at how to associate metadata with functions beyond the docstrings we learned about in Section 4. In the last video, one of our examples was a decorator that automatically passed all of a decorated function's arguments through an adapter. That's pretty cool, but what if we wanted each parameter to be handled differently? Sure, we could pass a whole bunch of adapters into the wrapper, but that becomes ugly and clumsy as we start dealing with functions that accept more parameters. What we'd really like to do is attach metadata directly to a function's parameters. Fortunately, that's exactly what function annotations are for. This example shows off Python's function annotation syntax. To associate a value with a parameter, we put a colon after the parameter name, and then we write an expression. That expression will be evaluated when the function is defined, and the result will be stored associated with the parameter name. We can also annotate the return value of a function by writing a dash greater than arrow symbol after the function's parameter list, and then an expression, which will also be evaluated when the function is defined, and the result stored associated with the word return. Because return is a keyword, there's no chance that it will collide with a parameter name. All the annotations are stored in a dictionary called bar annotations bar, which is an attribute of the function itself. As we can see here, annotations are not type declarations, though they could certainly be used for that purpose, and they resemble the typing syntax used in some other languages. They are arbitrary expressions, which means that arbitrary values can be stored in the annotation dictionary. They don't have any meaning to Python itself, except that it should store the values. That said, defining parameter and return types is a common use of function annotations. If we find ourselves using a tool that assumes annotations are type declarations, when we want to use them for some other purpose, we can use the standard no-type check decorator to exempt our function from such processing. Normally, this isn't needed because most tools which use annotations have a way of recognizing the ones meant for them. The decorator is for protecting the corner cases where things are ambiguous. Annotations combine well with decorators because annotation values make a good way to provide input to a decorator, and decorator-generated wrappers are a good place to put code that gives meaning to annotations. For example, let's rewrite that decorator from the previous video. We'll switch to only accepting keyword arguments just to keep the example relatively simple. So, the adapted decorator encloses the function in a wrapper. That wrapper only accepts keyword arguments, which means that even if the original function could accept positional arguments, they have to be specified by name once the function has been wrapped. The wrapper also looks for adapters in the function's parameter annotations and applies them before passing the arguments into the real function. Once the function returns, the wrapper checks for a return value adapter and, if it finds one, applies it to the return value before finally returning. When we take to consider the implications of what's happening here, they're pretty impressive. We've actually modified what it means to pass a parameter into a function or to return a value. Let's look at another example. Sometimes one or more of a method's parameters don't require any processing except to assign them to an attribute of self. Can we use decorators and annotations to make that happen automatically? Of course we can. Let's say that if a parameter is annotated with a string, the value assigned to that parameter will be assigned to an attribute of self, using the string as the name. And if the parameter is annotated with true, the attribute will have the same name as the parameter. If there's no annotation, or if it's not a string or true, nothing should happen. Again, for simplicity's sake, let's limit ourselves to keyword arguments. As we see here, annotations simplify all sorts of code-based manipulations of code. We're using basically the same techniques as in the previous example, but we're doing something entirely different with them. We've been looking at decorators as the primary consumers of function annotations, but that's not necessarily the case. Any code which uses function objects might be written to benefit from annotations. That means anywhere where we pass a function as a callback, we could potentially use function annotation data to make the code smarter about what it does with the function. Event handlers could be annotated with the names of the values the handler wants to receive. Dependency injection could be automated in a similar way. Constraint-based systems could be provided with the constraints that apply to each parameter. Probabilistic reasoning systems could be annotated with prior probability distributions. Parameters could be annotated with the proper user interface element to display in order to have the user input that parameter's value. The possibilities seem endless. Before we wrap up this video, I'd like to point out one thing that may be helpful down the road. Our example decorators that worked with annotations were all limited to keyword arguments for simplicity. If you find yourself wanting to do similar things, but needing to handle all sorts of parameters, the inspect package's signature function will simplify that process significantly. So, function annotations are a great way of adding metadata to functions, which can affect later handling of them in all sorts of ways. In the next video, we're going to look at class decorators and how they're similar and different from function decorators.